So we're going to talk about combinations of random variables. And in particular, we're going to still look at the expectations of those combinations. So now we'll suppose we have n random variables. And we're going to call those, say, x1, x2, up to xn. Now, each of these random variables will have a sample space, and it will have probabilities. And we're going to make things very, very simple and just suppose that each random variable has exactly the same sample space and exactly the same distribution. So the phrasing we use for this is we say they have an identical distribution. That is to say, the same omega and the same probabilities. Okay, so that says they all have, if you like, the same pattern. Not the same outcome necessarily, but the same distribution space. And the second thing we're going to have is that they are independent. And by that we mean that the outcome of one random variable has nothing to do with the outcome of another random variable. So the outcomes don't affect each other. Okay, now in statistics we use a shorthand for all these words here, and the shorthand is independent, I, and identically, another I, distributed. So IID, random variables, is just a very shorthand for saying we have an identical distribution, which means the same probability space, same sample space, and that they don't affect each other, they're independent, is a shorthand. And because they're all the same, we can just use one symbol for the mean and one symbol for the variance. So let's suppose that the expected value of any one of these is equal to mu. That's true for all I. And the variance of any one of these is equal to sigma squared, also over all of those. So that's just a shorthand for what we have in the distributions. And we can work that out. Of course, we have to know what omega is and what the probabilities are to be able to evaluate this, but all we're going to do is just say they're the same and they have the same means and variances. Okay, so a very commonly looked at quantity is a sample mean, and this is related to the sample mean, except it's a mean of random variables. So in the same way that a random variable has a distribution, the sample mean itself has a distribution. We define it in the way as before by simply adding up all the quantities and dividing by n. And of course our shorthand is to use this capital sigma sign. And now we've got an explicit index I, which runs from 1 to n, and we add up each of the quantities. Okay, so we're going to look at this, what you might call a sort of mean of the random variables. And in particular, we can look at the expected value of that quantity. Okay, now, some of what I write you'll be able to convince yourselves is true. I'm not going to do rigorous proofs for everything, but there are results which are worth knowing. So in this case, we have the expected value of x bar. And the way the expectation works is to take the expected value of this, we simply add all the expected values over here. So in this case, we have 1 over n times the sum of the expected values of each one. And as we said up here, the expected value of each one is equal to mu. And so we can write that as 1 over n. And then we have mu, plus, and on it goes. And the number of terms in that bracket is simply I going from 1 to n. I doesn't appear because they're all equal to mu. But we know we have n copies there. And so we have n values of mu divided by n. We simply end up with mu. Okay, so again, that's maybe no surprise that the expected value of the mean value of n things, which are all taking expected value mu, ends up with the same as we started from. Okay, and in a similar way, we could write down the variance, and so the variance of x bar turns out to be the sum, I equals 1 to n, and what we have here is the variance of the sum is the sum of the variances. But I've been a little bit sneaky because I put the 1 over n that used to be on the outside back inside the summation, but we still have the variance of the sum as the sum of the variances, and the constants, if you like, are all 1, so they're not going to affect anything. But if we look back at our previous results, where the variance of ax plus b was a squared times the variance of x, here we have a equal to 1 over n, and so we can substitute that in here. This is a squared, so 1 over n squared times the variance of xi, and that's 1 over n squared times sigma squared, I equals 1 to n, which is going to be sigma squared over n, because we have n copies of this, so that gives me n sigma squared divided by n squared gives me sigma squared over n. So just to pause here at this stage, we have the result that the expected value of x bar is the expected value of x, mu, but the variance of x bar is the variance of x divided by n. So what that says is the larger the sample size, the more values of n you have, the smaller the variability in the mean. Okay, the mean is going down at a rate 1 over n, so it's getting smaller and smaller and smaller. Okay, so this is kind of leading us to the sort of climax of the podcast. The very last point is, how is this all relevant? And in particular, what's the relationship between this story and the concept of a sample variance?